SwayamPrabha. Digital India. Educated India.
Now, I am going to do a second special case, okay. So, where we ask ourselves a question, okay, what happens when an entire row of the Routh's array is 0. Okay. So, we asked ourselves a question, what happens when the first entry in any row is 0, but let us say the entire row is 0, okay. Then what do we interpret from that? Okay. So, let me do an example to convey that point. Okay. So, let us consider a polynomial. So, that is why in order to essentially address his question, okay, I am going to give you a polynomial where the necessary condition is satisfied. See, I just deviated from it to just show you an example, okay, but that is why I wanted to show you that just by observation sometimes you can't what to say generalized for polynomials of order 3 and more, okay. So, let us consider the polynomial s power 7 plus 6 s power 6 plus 11 s power 5 plus 6 s power 4 plus 4 s cube plus 24 s square plus 44 s plus 24, okay, 7th order polynomial, okay, with 8 coefficients, okay. So, this is the polynomial, okay. So, of course, I could have taken a simpler polynomial and it would have appeared simpler, right. So, with lot of coefficients being 0, but I purposefully constructed an example where the necessary condition is satisfied, right. So, do you agree that all coefficients are non-zero and of the same sign? Yes. So, let us see, suppose if you have a 7th order system, okay, whose transfer function denominator polynomial is this, okay, then how do you find out whether it is stable or not, right. So, now we see the what to say usefulness of the Routh's criteria, okay, for control system design, right. Ultimately, we wanted, see this course is not about what to say general math, right. So, how do we apply those mathematics to control design, right. So, that is what we are interested in, right. So, let us construct the Routh's array and then like see what happens, right. So, let us write down the powers of S and you help me in constructing the Routh's array. Okay. So, what do? We fill in the entries in the first 2 rows, right. So, that is going to be 1, 6, 11, 6, 4, 24, 44 and 24, okay. So, that is what is going to happen. Now, can you help me with the numbers starting from the s power 5 row, what am I going to get? If I want to get this, like I multiply 6 and 11, subtract 6 and 1, divide by 6, what will that give me? 10. Then next entry, I multiply 6 and 4, subtract the product of 1 and 24, divide by 6, what will that get me? 0. Then what will I get here? I multiply 6 with 44, subtract product of 1 and 24, divide by 6, what will that give me? 40, right. So, that is about it, right. So, as far as the s power 5 row is concerned. Now, let us go to the s power 4 row. So, what would I get in the s power 4 row? I would get 6 as the first entry, then I would get 0, then 24, right. 24, correct. See, 10 times 24 minus 6 times null entry divided by 6, that gives me 24, right. Okay. Now, we go to the s cube row, what will I get? 0 and 0. So, now we have an issue, right. So, that we have come to a stage where we have the entire row of the Routh's array to be 0. What do we do? Okay. So before we figure out what to do, okay, let's learn a term, okay, which I am going to use here. Okay, what are called as radially opposite roots. Okay. So what can one mean by radially opposite roots? See, for example, let's say I take the S plane. Okay. So if I consider the S plane, and let's say I consider -3 and +3, that's a pair of radially opposite roots, right? So essentially you look at the origin, you draw a circle, right? So any pair of roots which lies on the circle, a relevant pair is a radially opposite pair, right? -3 and +3 form a radially opposite pair, right? Similarly, I can have, let's say 2j and -2j form a radially opposite pair. Do you agree? So that's a radially opposite pair, right? So on the imaginary axis, same condition holds true. Then I can also have -3 plus 2j and 3 minus 2j form a radially opposite pair, right? Correct? But the moment since we are dealing with polynomials which have real coefficients, we can have only complex roots that are, whose conjugates are also roots. So if I have such a scenario, I need to have -3 minus 2j and +3 plus 2j to also be roots of that particular polynomial. Okay. So these are three ways in which we can have radially opposite roots. Okay. So radially opposite roots can either be multiples of, in general, multiples of 2. They can occur as 2 roots or 4 roots. Okay. When can they occur as 2 roots? Of course, non-repeating pairs, right? So for example, if they lie on the real axis, okay, which are radially opposite, or on the imaginary axis. And if you have radially opposite roots essentially lying anywhere else, what will happen is that, like, you are going to have like this, right? -3 plus or minus 2j plus 3 plus or minus 2j. Okay, that's also a radially opposite set, right? So of 4 roots, okay, but essentially they are radially opposite to each other, right? Okay, so that's the definition of radially opposite roots. Now, when an entire row of the Routh's array happens to be 0, that implies that the polynomial is going to have radially opposite roots. Which of these patterns we are going to evaluate, okay, using the Routh's array? Is it clear what the implication is, right? So if we, let me restate it once again. If the entire row happens to be 0, this implies that we are going to have radially opposite roots. Okay, so that's what is the implication. Okay, so then how do we process this, right? So that's what we are going to learn. So let's learn what we do. So obviously I cannot proceed any further, right? So I'm stuck here in the S cube row. So what I do is that I construct what is called as an auxiliary polynomial. Auxiliary polynomial Ta of S is equal to, for looking at the auxiliary polynomial, I look at the row immediately above, the row in which I have all the entries to be 0. Okay, so let me write down the auxiliary polynomial, then we will understand how I wrote it, right? So here the coefficient 6 corresponds to S power 4, okay, and as I go one coefficient to the right, the power of S decreases by 2, okay. That's how we wrote down the coefficients of the Routh's array, because see, if you look at the very first row, the coefficient 1 corresponds to S power 7, 11 corresponds to S power 5, right? So and then like 4 corresponds to S cube, 44 corresponds to S, right? So as you keep on shifting one element to the right in any row, like in essence we are decreasing the power of the corresponding s term by 2. So in the auxiliary polynomial I start with 6 which corresponds to s power 4 and 0 s squared, so I just don't write anything, and then from s squared I just go to a constant term, s power 0 is constant, right. So the auxiliary polynomial becomes 6 s power 4 plus 24. Okay, that is the auxiliary polynomial. And once again I am just only stating the process and the results, like I am not proving anything here, right. So these have been well established. Okay, so and it so turns out that the roots of the auxiliary polynomial give us the radially opposite roots. Okay, so if you solve for the roots of the auxiliary polynomial, we get the radially opposite roots. So in this case, what do you think the radially opposite roots? If you calculate 6 s power 4 plus 24 equals 0. So that gives me s power 4 plus 4 equals 0, right. What is the solution of s power 4 plus 4 equals 0? Anyway, we'll come there. Okay, so as I told you, we are first interested in location. Okay, then we'll double check, right. So that's the general result. Okay, so if you have the entire row of the Routh array to be 0, what you do is that you look at the previous row, extract the coefficients from that, and then form the auxiliary polynomial. Then what you do is that you take the derivative of the auxiliary polynomial with respect to s. So we do dpas ds. So that's going to give me 24 s cube plus 0. That's it, right? When I take the derivative with respect to s. Do you agree? Okay. So what I need to do is that I will replace in the s cube row this 0 with 24. Of course, this 0 I will keep it as it is because the constant term is 0, right. So what I have done using this process is that in the s cube row the first element has been replaced with a 24, but the second element still remains 0. Okay, so I have to basically continue with that, right. So let's continue the process. Let's go to the s squared row. What will I get? If I go to the s squared row, what will I get? 24 times 0 minus 6 times 0 by 24. What is it? 0, right. Let's continue. And what will come here? 24 times 24 minus 6 times null entry by 24. What will that be? 24, right. So now what should I do? Yes, epsilon, right, what we just learned, right. So now you see that we have come to a case where only the first element is 0. There are non-zero elements in the row, right. So I replace the first element 0 by an epsilon and then continue, right. So what will I get? Epsilon being a small positive real number, right. So I will get epsilon times 0 minus 24 times 24, that's going to be 576 divided by epsilon. So I am going to get minus 576 divided by epsilon, right. And then that's it, right, in the s power 1 row. If I come to the s power 0 row, what am I going to get? I will just get 24, right. I have completed the construction of the Routh array, first Routh array. Now I look at the first column. Now if you look at the element above and below epsilon, what can you tell about their signs? The element above epsilon is 24, the element below epsilon is going to be negative in sign, right. Minus 576 by epsilon is going to be negative, right. So do you think there is a sign change above and below epsilon? So that implies that there are roots in the right of plane. So yeah, so from here to here is one sign change, and from here to here is another sign change, right, from minus 576 by epsilon to 24. So this implies that there are two sign changes which implies that 2 roots in the right of plane. Okay, yes. This 24? Yeah, you multiply 24 with 24, minus 6 with null entry divided by 24, right? So you get, is it clear? Okay, yeah. So I hope my calculations are correct, right? So, right, I hope this array is correct, right? So yeah, so that's what we get, like, so we get 2 roots in the RHP, right? And it so turns out that if you essentially solve s power 4 plus 4 to be 0, you will get minus 1 plus r minus j and plus 1 plus r minus j as the 4 roots. Okay, so the roots of, if you solve 6s power 4 plus 24, right, if you have a scientific calculator and solve this, or even you can process it as it is, right. So it's just s power 4 plus 4 equals 0, right, is it not? So how can I factorize this? Can I do this? Can I write it as s squared plus 2s plus 2? Yeah, please correct me if I am making a mistake. And this will become s squared minus 2s plus 2 is equal to 0, right. So this will be s power 4 and then the s squared terms will cancel off, right. Correct? Will I get s power 4 plus 4? Am I right? I say I am just doing on the go, right. So please stop me if I am making a mistake, right. So is this correct? So what are the roots of this polynomial? Minus 1 plus r minus j, right. So that's going to be 4 minus 8, yeah, you get minus 4. So this is going to be once again 4 minus 8, but this is going to be plus 1 plus r minus j, alright. So you see that we are going to have a case where we have 4 roots at plus minus 1 plus r minus j plus 1 plus r minus j, which are going to form a radially opposite set, right. So that's why we have this sort of a array. So consequently 2 roots are in the RHP, and of course the remaining 5 roots are going to be in the left of complex plane, because we have ruled out roots on the imaginary axis and there is no root at the origin also. Why is there, how can we conclude that there is no root at the origin? We discussed this point yesterday, right. Constant term is non-zero. See, if you have a root at the origin, constant term is 0, right. So but then like the constant term is non-zero here, right. So there is no root at the origin, right. So that's how we figure out things. Is it clear? Yes, please. No epsilon, okay. So minus 576 by epsilon times 24, right, times minus epsilon with null entry. So you will just get minus 576 by epsilon divided by 24. You divide by minus 576 by epsilon, cancels off, right. You are just left at 24, right, yeah. Okay. Okay. So these are 2 special cases which I wanted to do. Okay. Any questions on this? Okay. So please try out. Okay, like kindly try out more examples, and the more you try and more you come and discuss with me, like I'm sure both of us will learn together. Okay. See, I'm also trying out cases. Like you also try out cases, right? You construct examples where you have radially opposite pairs, roots on the imaginary axis, and then like a mix of both, right, roots on the imaginary axis and roots on the right of plane, right, and then like try things out. Okay, yeah, fine. So this is the Routh stability criteria. Now we are going to come back and we are going to see how to apply it, okay, to our case. Okay, so I am essentially going to talk about application of the Routh stability criteria to our case, right. So we are going to talk about the application of the Routh stability criteria. Okay. So we already did one example yesterday, right. So wherein we essentially looked at how do we get the feasible region of the controller parameters, right? So to give us closed loop stability, right? So that's something which we did yesterday, right? So if I go down, this is the example which we did, right? So we essentially use the Routh's criteria to figure this one out, right? So today let's do a few more examples. One more, maybe I'll just get started with one more example, and then we'll see how to go forward, right? So let's say, like I want you to design a negative feedback control system for a plant which has a transfer function like this, 1 by s squared minus 1. Okay, let's say we consider unity negative feedback. Okay, yes, please. 7 roots, yes, exactly. That's only for the auxiliary polynomial. I didn't get you. 2 roots for the sign changes. Yeah. So the 4 roots, 2 out of the 4 roots are going to be the right of plane, right? That's why you have 2 sign changes. They are accommodated, right? So that's why I made a statement 5 roots are in the left of complex plane for the original polynomial. See, the auxiliary polynomial, if you solve it, that will give you the radially opposite roots, right? So essentially you have 4 radially opposite roots, 2 in the left of plane, 2 in the right of plane. Okay. Now there are 3 remaining roots for the original polynomial. They are going to be the left of plane because you already accounted for two right of plane roots because there are 2 sign changes, right? That's it. So that's why I made a statement that from this I can observe that there are 2 roots in the right of plane, 5 roots in the left of plane. Okay. Can I please? Okay, let me repeat it. Okay. So did you? I hope the construction of the roots array is clear, right? And all of us can agree that there are 2 sign changes, right? 2 sign changes means there are 2 roots in the right of plane, right? So yes, please pay attention. No. So you can see that the auxiliary polynomial is of 4th order. Okay. And so you are going to have 4 radially opposite roots. Here we can see that the 4 radially opposite roots are going to be like plus or minus 1j and 1 plus or minus j and minus 1 plus or minus j, right? So this is in the LHP, this is in the RHP, right? So is it not? So there are 2 roots in the right of plane, 2 roots in the left of plane for the auxiliary polynomial, right? So that which constitutes a radially opposite set. There are 3 remaining roots which are once again going to be the left of plane. Why? Because if you look at the epsilon entry and you look at the entries below and above epsilon, since there is a sign change, we conclude that there are roots in the right of plane. Okay. So if the first entry is a 0 and you replace it with epsilon, we discussed that there are 2 cases, right? If there is no sign change, that indicates a pair of roots on the imaginary axis. If there is a sign change, then roots in the right of plane. Okay, that's the criteria used.
These 4 roots are the roots of the auxiliary polynomial. So, what are the roots of the original?
The roots of the auxiliary polynomial or the forms a subset of the roots of the original polynomial. You can factorize it, like so. Yeah, I'm not proving it. Okay, I'm only using the result. Okay, good question. How do we show that the roots of the auxiliary polynomial are the roots of this one? You can prove it in general. Okay, so I'm not doing it here. But if you want to convince yourself, you can substitute the roots in the polynomial. You will see that it will go to 0. Right? You can do that check. Right? Yeah. That's the best way to check. Right? Whether some value is a root or not. Right? Yeah. Yeah. 7 roots, right? Totally there are 7 roots, 2 roots in the RHP, right? Which are these? Remaining 5 roots in the LHP, out of which 2 are minus 1 plus or minus j. I don't know about the other 3, okay? Yeah, but of course I can write here, okay? Of course, since I know the answer, right? So now I'm going to write the roots minus 1, minus 2, minus 3, minus 1 plus or minus j, 1 plus or minus j, okay, like so. Of course, that's how I constructed the polynomial. It's just not that, you know, I just wrote the polynomial arbitrarily. I used the poly command in MATLAB, right, to generate this polynomial, okay, by trial and error, okay, yeah, fine. Yeah. So please check, you know, like all the questions that you are getting are very common, which I also have, okay, and I have essentially figured them out, right. So I want you to do more examples to essentially figure these things, okay, that's how we learn, fine, okay. So I think what I'm going to leave you with homework is that, like, look at this plant, okay. The plant transfer function is 1 divided by s squared minus 1. Obviously it's an unstable plant or system, right, because you have roots at plus 1 and minus 1. Try to stabilize it, okay, using P, Pi, PD, PID, whichever controller works, figure things out, right. And then, like, use the Routh stability criteria to essentially figure out, you know, like which what ranges of controller gains or parameters would give you closed loop stability, okay. So we would come back in the next class and then, like, look at closed loop performance. Now that we have figured out how to evaluate closed loop stability, we would figure out how to evaluate closed loop performance, right. And see, if in many references you will find the term absolute stability, okay. The condition that we need to have all the roots of the closed loop poles of the closed loop transfer function in the left of complex plane is what is called as absolute stability, okay. Later on we will look at what is called as relative stability. That is, we want roots in the left of complex plane, but even a little bit farther to the left, okay, from the j omega axis. As I discussed already, you know, like, poles are once again an approximation, right. So you can have unmodeled dynamics, parametric uncertainties and all, so the poles can shift a little bit, right. So I don't want a pair of poles at minus 0.01 plus or minus j, right. That's going to be very, very close to the imaginary axis, right. So relative stability talks about those questions, okay. So can we push the poles a little bit farther to the left, but there is a price to pay, okay. We will see what is the price and when we look at relative stability, okay. So we will stop here.